Welcome to e-Pathshala lecture series in computer science. This is the subject called cloud computing. Today we are going to discuss about snapshot. So, our learning objectives are what is a snapshot, and then we will look at the possible applications of a snapshot, and then we will see what are the different mechanisms that can be used to obtain a snapshot. In specific, we will look at one algorithm called Chandy-Lamport's algorithm and then summarize the module. So, in the last class, we looked at the mutual exclusion. Mutual exclusion, what are the requirements we saw, and then we looked at the mutual exclusion algorithms, two algorithms in specific. One is called the leader based algorithm and the other is the ring based algorithm, and then we looked at the mutual exclusion in cloud. Today we will look at similarly in snapshot. Let us first take an example to see how things are, what are the requirements for which this snapshot is needed. Let us think of a bank which has different branches in different states or cities, and let us think of an account. That account can be accessed from various branches. We can imagine this to be a joint account where multiple people are accessing, or even a single account where the account is highly active and there are multiple accesses to the account. Now, if we need to keep track of the account at any point in time, the employees of the bank need to understand whether it is possible to allow a transaction through, then we need to know the state of the account, combined state of the account, which will be from all the states or all the. So, now assume that the mechanism using which the employees of this bank are interacting are message passing. This message can be passed using a, say, a mobile phone or a mail or whatever. Now, the job here is to see how to understand the overall situation of the of this account. So, what are the requirements of the of these employees which will give them the overall idea? The idea of the state of the account, which means that how many transactions have been done, how many withdrawals has happened, all these information should be available with the employees at any given point in time. So, therefore, a simple way of naive way of looking at it is, why don't we ask all the employees to note down the situation of their side of the account at any point in time, and then send these information to one coordinator who will put all these information together and will generate the overall state of the account. So, to be able to do that, to be able to have implement such coordinator based mechanism, what is it that we need? We simply need a predefined clock with each process, so that we can say that every day morning at 8 o'clock you take down the state of the process of the account in at your end and send that state to the coordinator. But this time has to be a well defined, well organized time, so that we can have a proper picture of the of all the states. Unfortunately, we know that distributed system, it is not possible to have a time. The concept of time is very difficult in a distributed environment, and we know that cloud has data centers which are in different places, and therefore obtaining the concept of time is difficult because of the geographical differences in the data centers. So, what are the exact problems? The problem is the absence of a global clock, where there is no concept of a global clock in a distributed environment. we looked at in earlier modules, we looked at how to do clock synchronization using physical clocks, but we saw that it is not a foolproof mechanism because of two factors. The clocks drift, they do not have the same rate of change over a period of time. So, therefore, they give different times even starting from the same point, and unfortunately they drift in different manners and different ways. So, the skews, which are the differences in times between two synchronized clocks, becomes too high, and therefore, we lose the concept of synchronization. We saw that a solution to this is to synchronize more often, but we must remember that the amount of time we spend for this kind of work is very important, and we should not be spending too much of time. So, therefore, we assume, in general, we make an assumption that there is no concept of a global time. The other problem that we have to be able to create a simplistic solution to our problem is the communication channel. We use the underlying network to send and receive messages. In our example, it is the mobile phone service providers and the mail service providers, and they are at best unreliable. So, therefore, we are not sure whether messages will be delivered at what gap, whether messages will be delivered in sequence, whether messages at all will be delivered or not. So, with these problems, we understand that it is not possible to use a time as we understand looking at a clock. So, as a solution, we looked at two possibilities. One is called the Lamport's logical clock, which we will just now take a look at again, and another is called the vector clock. So, let us take a quick look at what is a Lamport's logical clock. This diagram is called a space-time diagram. In this diagram, we see that there are three processes, P1, P2 and P3. These processes, this is how the time is going, and these processes continue, and each of these are called an event, and the events happen for various reasons inside a process. Like in P1, E11 is a local event, something is happening over there. E12 is a send message event, M1 is a message, and E24 is the corresponding receive message event. So, this is the timing space-time diagram, and we have the logical clocks. Each process has its own clock, and they increase it and they synchronize with respect to each other. So, if we look at these events, we see that we can have a happen before relationship among these events. For example, E11 and E12 are two events which are happened before. We can clearly say that LC1 is less than LC2, and therefore, E11 is happened before E12. Similarly, we can say that E25 and E32 are two happen before relationship, because this is a send and receive message. Similarly, we can say E12 and E24 are happen before relationships, and E11 and E33, because the happen before relationships are transitive in nature. But Lamport's clock has its own problems. What is the problem? Let us look at some other examples. For example, E11 and E21. This is our E11 and this is E21. The clock values are identical. So, therefore, can we look at the clock values and say the relationship between these two? So, in this particular case, the clock values are identical, therefore, we can call them two concurrent events, because the clock values are not differing. In another example, let us take E13 and E32. Here, the clock value is 3 and the clock value is 6. So, since 3 is less than 6, can we say that E13 has happened before E32, unfortunately Lamport's logical clock does not allow us to do that. So, therefore, we can say that if an event has happened before another event, the logical clock should be the one having occurring before should have a less value, but looking at the clock value that this value is less than this, therefore, the events have happened before relationship cannot be determined in a logical clock. This is another example where we can see the same thing. So, as a result, we moved on to what is known as a vector clock. So, here is an example of a vector clock. In a vector clock, the values will be 3, 0, 0. So, in a vector clock, each process is represented by one value, and a clock will have n entries in a vector which represent the n processes in the system. And here we can clearly correlate the time, the vector time, and we can determine the happen before relationship. So, these are the two clock mechanisms that are used in a distributed environment and therefore in cloud. Each one has its own advantages and disadvantages, and we can decide which one to use. Now, how to use these clock values with respect to problems that we have defined right at the beginning? If we take this example, we can easily use the clock values to determine which are the points where the the state of the account should be noted. So, our problem is that we can independently go to each branch in each state and obtain the clock value, but we do not know how to do it because of the absence of time. We can figure out a mechanism where using either the logical clock or the vector clock, we can give instructions to each process when exactly they are supposed to take the picture, take the current situation. So, this is what is known as a snapshot. So, we are trying to take a snapshot of the overall system by taking separate snapshots, smaller snapshots of each process. So, what is a snapshot? A snapshot is a picture of each component in the environment, using which we can obtain an overall picture. So, snapshot is nothing but a photograph. Having understood this, let us look at the use of snapshot. In the earlier example, as we have already said, we can easily use a logical clock or a vector clock and determine the states of each account, of one account in each branch by determining that this is how the this is when a corresponding snapshot should be taken. There are various other examples where snapshot is used, like when there is a crash in a distributed system, we need to recover from the crash, and to be able to recover from the crash, we need to put back the system at a point in time, at some earlier time where all the systems were perfect and in coordination. So, we can take a snapshot of every now and then keep these snapshots, and whenever there is a disaster, whenever there is a crash of the system, we look at the earliest, the most recent snapshot that we have, and we restore the system back to that point. So, even for a processing in a distributed environment, particularly in a distributed environment like cloud, we do not understand when a specific processing has stopped or whether a processing computation has completed. So, we can take a snapshot to make this decision that a computation has completed. So, to be more precise, in cloud we have the applications running in different data centers and different servers. We have services that are being offered from different data centers, and therefore multiple locations, geographical locations. All these require events to be executed concurrently, and as soon as we have concurrent events, we have a problem of not understanding what is the situation, what is the overall situation. To be able to understand the overall situation, we have to be able to take a global photograph of the system, and that is very important in cloud. So, let us now look at what is a global snapshot. So, essentially a global snapshot is the overall picture. If I have an overall picture, I have a global snapshot. Now, how to obtain such a global snapshot? The method that we are going to discuss obtains it by taking a snap of or a photograph of different components which are located in different places in an independent manner. What is an independent manner? That we should not get a specific instruction from one specific location. We should be able to do it after doing some other work that we are doing. That means that we should not stop the system, we should not stop all the activities and then take a snapshot. We should continue doing the normal work without hampering the normal work. If I am able to take a local, these are called local snapshot, each process will take a snapshot of its own locality, and we should be able to put all these together and come up with a global snapshot. So, what is required? This is also called a global state, and what is required is that individual state of each process in a distributed environment is obtained, plus what we should not miss is that we also need to take the individual state of each of the communication channel. It is very important that we understand the communication channel and its role in what we are trying to do. So, let us take a look at what is the importance of communication channel. Here is an example, again another space-time diagram where there are two processes P1 and P2. P1 has 1000 rupees and P2 has 1000 rupees. So, the total money is 2000 rupees in the system. Now, assume that P1 is sending some money to P2, 50 rupees to be precise, at time T1 in place A. So, therefore, the money becomes 950 in P1. Similarly, at B, P2 is sending 500 rupees to P1. P1 receives this money and its total becomes 1450, and P2 receives this money at D and its total becomes 550. Overall total remains 2000. So, we started with the 2000, we completed with the 2000, there is no surprise in this. Now, where is a surprise? This is a surprising situation. If we decide that x1 and x2 will be the two points where we would want to take the snapshot, then look at x1, the value is 950 because I am yet to receive the 500, and look at x2, the value is 500 because I have given the 500 and I am left with 500. And if we take a snapshot at this point in time, then our overall is 1450, and that is not the total amount of money. So, we need to get what is known as a consistent cut. First, let us understand what is a cut. A cut is any arbitrary line through the space-time diagram. This line should join any random points. In this case, example 2 points. In fact, if there are n processes, then the cut should be able to join n points across each process and divide the overall system. This cut will divide our space and time diagram into two parts. One will be the left of the cut and the other will be the right of the cut. Now, this cut is very important because this cut tells us this is the time where I am dividing my system into two parts. Cut is consistent when we say that all the messages that are received on the left of the cut, that means a message cannot be received unless the message is sent. So, a message that is received to the left of the cut should also be sent to the left of the cut. So, if we are able to do that, then it is a consistent cut, otherwise it is not a consistent cut. A consistent cut also represents a global state. Let us look at the example. So, here is our example of our earlier example. Now, look at this, x3 and x7 is a consistent cut. All the message received have the sent to the left of the cut. Let us take another example, x1 and x5. Here, two sent messages are there, but the received events are to the right of the cut, but still our consistency situation is not disturbed because no received messages is to the left of the cut. In another example, we have a similar situation. The two send events are there on the left and the corresponding receive events are there on the right. But here is a cut x3 and x4 where you see that we have, this is the receive event of this message 500 rupees from P2, but the sent event is not included to the left of the cut. So, this is a message, BC is a message whose receive event is to the left of the cut and whose sent event is to the right of the cut, and therefore, this is a inconsistent cut. So, let us now look at a formulation of our algorithm to obtain a global state and a consistent cut, so to say. So, the task is to be able to obtain a consistent global state. We need an algorithm to determine the cut in the system. The cut is used to obtain the snapshot, and this snapshot should give us a global state, a consistent global state. So, this is the Chaudy-Lamport's algorithm. Let us first look at the assumptions of the algorithm. There are n processes P1 to Pn. One of these processes will act as an initiator. Somebody has to start the process of taking a snapshot. So, that particular process we call an initiator. The processes are communicating through one-way channels. That means, it does not mean that two processes cannot receive messages from both sides. It means that each communication will be represented using a channel, and these channels will be one-way channels. Also, the channels should be first in, first out, which means that the messages, the order of the messages in which these are sent, the receiving side will receive these messages in that same order. The order will not be differing. We also assume or understand that there is no global clock and there is no global shared memory. That means, I cannot store the value somewhere where it will be read by other people. I have to send it in a message to the other process. And we use something called a marker, which is a special message, which as soon as I receive a marker, I understand that the other process is trying to tell me something. We have used a similar mechanism in our election algorithm, if you recall. Now, recording a state involves noting down for the process all the messages sent and received by this specific process to any other process. So, these are the conventions. We denote Cij to be a channel where since the channels are one way, the Cij will denote a channel which will allow Pi to send a message to Pj. Similarly, if we have a Cji channel, Pj can send a message to Pi. We assume that all the processes are white at the beginning, and our objective is to change the color of all processes and the channels to red. A process turns red when it has recorded its state, and a channel turns red when it has transmitted and through it a marker has gone and is received on the receiver side. So, the color of the channel will be changed only by the receiving process. So, every channel will have two processes involved, and the color can be changed, the channel color can be changed only by the receiving process. The process records its state and records the channel and also changes the color, and the recording for a process stops or for an overall system stops if all the processes and the channels have changed the color. So, here is the algorithm. In step 1, a process Pi starts, it is the initiator, it starts recording the state and changes its color to red. In step 2, for all its outgoing channels, it will send what is known as a marker. It will send a marker. And in step 3, we start recording the incoming messages on each of these channels, and we continue recording it. We have not completed the recording yet, and we will stop recording a channel only when a marker comes through that channel, marker is received. So, as soon as we have received the marker, we stop recording that channel and we change the color to red. So, let us quickly go through these steps once more. I have an initiator which initiates the recording, and it first records its own state. So, so far how many messages have been received and sent is recorded along all its incoming and outgoing channels, records and changes its color, indicating that I have recorded so far, and then it sends a marker along all its outgoing channels. So, incoming channels it cannot send anything, it can only receive. Outgoing channels it can send. So, it sends a marker along all its outgoing channels, and then it starts recording now. Now, whatever more messages are coming through its incoming channels, it does not refuse, it continues adding these messages only when it receives a marker along this channel. That means, on the process on the other side must necessarily send a marker along this channel. Only when it receives a marker, it stops taking in any more messages in the current recording and declares that the channel is red, turns the channel to red. The process which receives a marker through a channel, the process is everybody is sending the marker. So, every process will receive the marker. If this is the first time a marker is being received by Pj on a channel Cij. So, Pi is sending to Pj a marker along the channel, and this is the first time. Pj has not received a marker so far. So, it will record its state and it will change its color to red. And also, this is the time when it marks this channel Cij to be empty and changes the color of the channel to be red. So, I receive a marker along a channel, I record my state, I change my color to red, and I change the incoming channel's color to be red. And then I repeat step 2. What was our step 2? Step 2 was this: while there is an outgoing channel, in this case Pj's all outgoing channels, it sends a marker. And then it repeats step 3, and here is our step 3. Step 3 says, I keep on recording my incoming channels messages. I wait for a marker to come. As soon as the marker comes, I stop recording and I declare that channel to be empty and red. So, this is our mechanism for Chandy-Lamport's algorithm. So, what in today's class, what we looked at is we looked at the need for logical and the vector clocks. We looked at an use of logical and vector clocks in what is known as a snapshot or a global snapshot. We saw that a global snapshot is equivalent to having a consistent cut, where cut is nothing but arbitrary set of points across the space-time diagram which will be called inconsistent under certain circumstances and consistent if to the left of the cut all the messages received have also the sent to the left of the cut. We saw that a global state and a consistent cut are quite identical in the sense that if I have a consistent cut, I can have a global state. And then we looked at the an algorithm which is called Chandy-Lamport's algorithm, which helps us getting a consistent cut along the space-time diagram. This is irrespective of the number of processes that are available, and therefore it can be applied to any situation or any distributed environment. So, in the next class we will continue this discussion and we will look at an example for Chandy-Lamport's, and we will see exactly how to apply Chandy-Lamport's algorithm in the in a actual real life situation. These are the references. Thank you.